Okay, for number 1, if you decrease the volume, which rate will be affected more?
Decrease.
Yeah. Will it increase or decrease more? Yeah, so when you decrease the volume, both rates are going to increase, but the reverse rate will increase more because there are more particles on the product side. For number 2, we want to know what happens if we dilute this. So if you dilute it, the rates will both drop. Agreed? So since I've got 1 particle on the reactant side and 3 on the product side, which one will respond more?
Reverse rate.
Yeah, so the reverse rate will decrease more than the forward rate. Okay, let's take a look at number 3. Show the reverse and forward reaction rates response to a sudden compression at T1. Okay, so these are all gases. Oops. There we go. We've got 3 reactants, 2 products. Okay, so when you compress something, both rates will increase, but it looks like the forward rate is going to increase more. Agreed?
Yeah.
Because it's got more particles. Okay, so this is what it would look like at the stress-ish, right? And then eventually they will both be the same, but they will be more than they were at the final equilibrium than the initial. And then over here, you've got your forward rate peaking. So that's going to increase more. And then it's going to level off at T2. So it's going to come down here and then level off. And then this one will also rise up to meet it. Something like this. Okay. All right, any questions on that? That was half of this section, okay? The other half of this section is on temperature changes, okay? Okay, so let's do the temperature changes, and then I'm going to have you guys work on this homework assignment before we go on and do anything else. So let's take a look at temperature changes, and then endothermic and exothermic processes are going to affect which direction we shift to. So they're going to be giving you a delta H value either after the equation or within it. Okay, so a system at equilibrium will respond to a change in temperature by shifting to remove some of the added kinetic energy, meaning the added heat, or to replace some of the removed kinetic energy. Okay? So let's go over what happens with an endothermic process. Here in the sample problem, we are heating it. So that means I am increasing the temperature. If you take a look at the delta H value, it's a positive delta H value. So that means this is an endothermic process. And then what I would do is I would put plus heat on the reactant side just to remind you that it's endothermic. The reason I would do that is because if you're increasing temperature, if you can identify where the heat is, if it's on the reactant or the product side, you can predict which direction you will shift to. So if I'm adding heat, which is a reactant, in an endothermic process, anytime you increase the concentration of something, don't you move to the other side, you shift away from it. So here you're going to shift to the right. So anytime you add heat to an endothermic process, you will always shift right. And the reason you're shifting right is you need to consume some of this added heat and help you get back to equilibrium. So that means you will convert some, emphasis on the word some, of the added kinetic energy, which is the heat, into potential energy. So now it will be stored in the products, okay? The other questions that they're going to ask you are, what's going to happen to the concentration of each substance once equilibrium is restored? Well, if you shift to the right, that means that NO, my product concentration, is going to increase, and you're going to consume N2 and O2 to shift right. So N2 and O2 concentrations will decrease. Okay, let's take a look at the next page. Next page is the exact same reaction. Here we're just cooling it. So that means we're dropping the temp. So if heat is a reactant and I'm going to remove some heat, right? Because this is endo, this is positive. Then I need to shift in its direction to bring some of it back. So anytime you remove heat in an endothermic process, shift left. Move in its direction to produce some more heat. So that means you're going to convert the potential energy that's in the products into kinetic energy, which is heat energy, because they'll cause them to move more. When I shift left, the concentration of my product will go down, and the concentration of my reactants will go up. Okay? Let's take a look at one more problem. At the bottom of the page, they give you a practice problem that's exothermic. Okay, so if you come down here, they've heated this exothermic reaction. Here my delta H is negative. So what I'm going to do is I'm going to go ahead and I'm going to write plus heat on the product side to remind me where the heat is during exothermic processes. If I'm adding more heat, that means I need to shift away from it to consume some of it. So we're going to shift to the left. And we're going to convert some of that added kinetic energy into potential energy. So now it will be stored in the reactants. That means the concentration of SO2 and O2 are going to go up, and the concentration of SO3 is going to go down. Number 2. We're cooling this reaction. Notice they gave us a thermochemical equation with the delta H value inside of it. So this is my delta H. Since delta H is written on the product side, that means that this is also an exothermic process. Normally this delta H would be written as negative 17 kilojoules per mole. If I'm cooling it, that means I'm going to remove some heat, which is on the product side. I need to restore some of that lost heat, and I will do that by shifting in its direction. So shift to the right. When you shift to the right, you will convert some potential energy, which is stored in the bonds of the reactants, into kinetic energy, which will bring the heat up because everything will be moving more. And then the concentration of H2 and the concentration of I2 will take a dive. The concentration of HI will increase. Yeah? Okay. All right, now, let's see what else there is to talk about. I'll let you guys read through this on your own. There's really not much to highlight. The only thing that I want to highlight here is that when you increase the temperature, the endothermic direction is generally affected more. So let's look at this curve. This curve going from left to right, or the forward direction, has a really large activation energy, right? So this direction is my endothermic direction. You can see that I have this huge amount of energy that I have to get over in order to convert reactants to products, as opposed to the exothermic direction is going in the reverse. And this reverse activation energy is nowhere near as high as it is for an endothermic direction. So that means when you increase the temperature, you're going to notice a greater change in the endothermic rate than you would in the exothermic rate, okay? Because it's harder to convert reactants into products in the endothermic direction, and it will benefit more from an increase in temperature. And they tell you all of that right in here, okay? Okay, let's take a look at the next page. Let's take a look at these sample problems. They want to know what's going to happen to the forward and reverse rates when we heat this reaction. This is endo. That means heat is a reactant and we're adding more. So the endothermic direction is affected more when we increase the temperature. So since left to right is endo, that means you are going to increase that forward rate significantly more by increasing the temperature than you are the reverse rate, okay? Let's take a look at the other sample problem at the bottom of the page. Down here, same process, delta H is positive, endothermic in this direction. Here's my heat. Here we are cooling it, okay? Since the forward direction is my endothermic direction and I'm dropping the temperature, that means that direction will be affected more. So here you can see that the forward rate dropped significantly more because it's the endothermic direction, okay? Let's take a look at the last set of practice problems. For number 1, we are heating this reaction mixture, which is exothermic. So I've got heat as a product, so I'm adding heat. This opposite direction, the reverse direction, is my endothermic direction. So if I'm heating it, which rate will increase more? Forward or reverse? Which one's the endothermic direction? The forward is exo. So the reverse is? Endo. So that means the reverse rate is the one that is going to increase more. Okay. If you take a look at number 2, here we're going to cool this. They gave us the delta H value inside the reaction. So this is heat. We are removing some. This direction is my endothermic direction. Which rate will decrease more? Forward or reverse? It's whichever one is the endo. Okay, so the forward rate will decrease more because that's the endo. Okay, let's take a look at number 3. Okay, here we are increasing the temperature at T1, which is right here. My reaction is exothermic in the forward direction. So this direction is exo, this direction is endo. Anytime you increase the temperature, you will increase the rates of both, but which one will have a greater increase in rate? The endothermic. So that means this reverse one will have to increase more than the forward. So it would look something like this, okay? Eventually, at the final equilibrium, both of them will be the same, right? They'll both have increased. The reverse will come down a little bit to meet the forward. And so that means when you go over here to plot it, you need to have that reverse one spiking. And then at T2 is when it's going to come down and level off. So it's going to look something like this. And then the other rate will come up to meet it like this. Okay. Last thing to talk about is the Haber-Bosch process.